All right. Today focuses on these two. Some of it should be a review in the sense that we've already talked about esters, but it's been a while, so how I've got the board set up right now is a little bit of a review, maybe one new thing, but I've color coded it to try to help. Hopefully you can see the colors. If we look at functional groups, those I have boxed in red are going to have acidic tendencies, or there are acidic functional groups. And what that means is if you see that molecule or a functional group in a molecule that has that property, it's going to react with a base. Typically, what base are we going to use? Sodium hydroxide, which you might also just see as hydroxide. This key functional group, which I have boxed in green, the amines, it's boxed in green because it has basic properties. So what that means is opposite of acids, a basic functional group is going to react with an acid. And the acid-base reactions aren't really synthetics. In other words, we're not making a new molecule. We're kind of just changing the form of the molecule. That's really important for medicines, drugs, and in laboratory when we do extractions and whatnot. And then lastly, these two functional groups boxed in blue are boxed in blue to indicate that they are susceptible to hydrolysis. So hydrolysis means reaction with water. It's a little bit different than hydration like we did with alkenes, hence the name hydrolysis. These hydrolysis reactions can be catalyzed by acid or base, and of course water. And the conditions, meaning how it's catalyzed, can largely affect the structure of the products. So that's what we have to practice today. To get going, as always, we're going to review. So would we say we can recognize this as, first off, a carboxylic acid, and second off, is it a 4-carbon acid?
Which one?
1, 2, 3, 4-carbon acid, and so we would name it butanoic acid. This one you should have seen enough now that you can just say benzoic acid. That one's not an acid at all, but an alcohol, and 2-propanol, also known as isopropyl alcohol. Well, we're on the alcohol theme. This is not an alcohol at all. It's up there today just to make sure we've said it once or twice or 10 times. As a functional group, it's a phenol, and phenols are not alcohols. They do have some properties of alcohols because they both have this polar OH group. But the main property that differentiates phenols from alcohols is phenols are also acidic. So those are your two functional groups that are going to be acidic. And then onward to these three molecules, which would all be amines. So all three of these molecules are amines. And as amines, boxed in green, they are basic. And then we would also subclassify amines as either being primary, secondary, or tertiary. And we should be pretty well versed in that. Why is that one tertiary? Because it has three carbon groups on the nitrogen. This one's secondary because it has two carbon groups. And this one's primary because it just has one carbon group. And then in naming amines, we just name the carbon units as groups followed by the word amine. So this one would be benzolamine. That one would be ethyl isopropylamine. And that one would be triethylamine. So you could foresee questions like, which type of amine does the nitrogen not have an H? And you would answer the tertiary amine. Which type of amine does the nitrogen have two H's? You would answer the primary amine. A secondary amine, the N has only one H because it has two carbon groups.
So do we only name them primary, secondary, and tertiary amine? Is that sufficient to do the naming?
That's the classification of it.
Could you help me with the names of all those three? I forgot.
That's a benzyl group. So that's benzolamine.
Okay.
That's an isopropyl group. That's an ethyl group. So that's ethyl isopropylamine.
Okay.
And that's three ethyl groups. So that just becomes triethylamine.
Okay, thank you.
And as hopefully a quick review, would we say this molecule is an ester?
Yes.
And so as ester, we should remember that esters are composites of acids and alcohols.
Mm-hmm.
And so if you're trying to name this ester, you will find the ester bond. And you would recognize this is the alcohol remnant. This is the acid remnant. And that alcohol is which alcohol?
Isopropyl.
Isopropyl, and this acid is
A benzyl.
benzoic, correct? So to name the ester, we would say isopropyl, and then benz, and the ending of ester is 08 or 8. So that's isopropyl benzoate.
Cool.
So that should basically be a review. And of course, don't get tripped up if someone shows it like that. Is that still isopropyl benzoate? Yes, it is. But if you see this, that's a totally different molecule.
Yes.
That's a totally different molecule because now this is the ester bond. This is the alcohol side. That's the acid side. This would technically not be a true alcohol because it's a phenol. But at any rate, we would name that phenyl. And then this acid would be
isopropanoate.
1, 2, 3, 2-methyl propanoic acid. So you would have 2-methyl propanoate. But you could say isopropanoate. I would get what you meant by that. So my point being, I'm not going to ask you to name something that complicated likely, but it's important to recognize which side of the ester is which. Alcohol, acid side. Up here, it's alcohol, acid. And so hopefully this will be a review. If the question is, how do we make this ester? Well, realizing that an ester is a composite of an alcohol and an acid, and this is the alcohol side, you would react isopropanol, and that's the acid side, and that's benzoate, which came from benzoic acid. So you would react benzoic acid and isopropanol, and that would make this ester. And really importantly, going to make that ester, what would be the byproduct? This C is losing OH, and that O is losing H, and so the byproduct would be water. And when we did that, we called it Fischer esterification. And the finding of water just helps you realize that this O is going to connect this C to make your ester. For what's coming up, realize that this equation's really catalyzed by acid, but it's also reversible. So if it's reversible, can of course esters react with water? And if an ester's reacted with water, do we get back our acid and alcohol? And so we would call hydrolysis of an ester. We would call this direction synthesis of an ester using Fischer methodology. Going to the right, Fischer esterification. The reason that's a relevant review is amides are just the nitrogen analog of an ester. Probably those words don't mean much to you, but if we go with acid alcohol makes ester, and an amine is sort of like an analog of an alcohol where N replaces O, then what will an acid and an amine make? An amide. In that, if you have the right catalyst, which we're going to always use DCC for making amides, DCC just promotes removal of water. So again, if we want to find the water from between these two molecules, we would say the C of the acid is going to lose the OH, and the M loses the H, and thus what are we going to connect on the other side? The C, which lost the OH, gets connected to the N, which lost the H. So if you connect that C to that N, you'll have your amide. And then what is the byproduct again? So
And
amide.
And that's called an amide?
That's an amide.
Okay.
For ester functional group, we have that bonding pattern. And for amide, we have that. Sometimes these R's are H's. Sometimes they're carbon groups. When we go to name the amide, kind of like esters, in that you're going to start by naming the carbon groups, if there are any, on the nitrogen. Then you name the carbon groups prefixed with N. So this is N-ethyl. And then this group is N-isopropyl. And then the acid, in this case butanoic acid, changes to butanamide. So all amides are going to end in amide. And the prefix in front of the amide comes from the carbon group of what was the acid.
So we don't have to number them for location. We just have to put like the N.
That's correct. This designates it's a group on nitrogen. So step one, would we recognize that as an amide? So how do we recognize an amide? This all goes back to our carbonyl group. So the carbonyl group is a C double bond O. And various things can flank it. So if I say one or more of those R's are H's, what functional group do we have? Aldehyde. If both of these groups are carbons like that, now we have a ketone.
Ketone.
This R group is OH. Now we have an
Carboxylic acid.
If this group is OR, now we have an
Ester. An ester.
And if this is NR, now we have
an amine. No, an amide. Amide.
And in amides, do these have to be R groups or can they be H's?
Either or.
Either or. So what makes this an amide? Just that? Nope. Just that? Nope.
No.
The combination of this connected to that. And you don't want to confuse amides with amine. So what makes this not an amide?
Because it just has the nitrogen and the 3 R's.
And it does not have a C double bond O next to the nitrogen. So if we recognize this as an amide, the obvious next question is, which amide is it? If the groups on the nitrogen are hydrogens, you don't have to name them. So you don't say anhydro or N anything. If it's hydrogen, you just don't do anything. So do we have to do anything with those two H's in our name? Do we still have to recognize it's an amide? And what do all amides end in? And what's the prefix of the amide? Where is it derived from? Whatever was the carboxylic acid. So which acid is this derived from? That one. And what do we call this acid? Benzoic acid. And what happens to the OIC? The OIC changes to benzene. If this did have two carbon groups on it, like that one, now what would we call the amide? If it just had one carbon group. It's still a benzamide because this didn't change, but now what group is that? N-butyl. So that's N-butyl benzamide. If we stick another group up there, like your favorite, now it's N-butyl and butyl benzamide. Next up is very important because it can be particularly confusing. You don't have to know this, but I'm going to put it up there to help you. That's DCC. It stands for dicyclohexyl carbodiimide. It's just a very potent water scavenger. So if DCC sucks up water, you get DHU. You don't need to know all those acronyms. I'm just putting this up there to make sure we plant the seed that this helps amide formation by sucking up what? Water. Because again, is this all potentially reversible? And if you can somehow scavenge the water, you're going to promote movement of the reaction to the right. Just for trivia, DHU is dicyclohexylurea. So, fun facts for the day, that is urea. So, as we should all know, because we're all alive and we all pee, that is the byproduct of protein metabolism, which is toxic to our bodies, so we have to excrete it out in the urine, hence the name urea. So again, you don't have to know any of that. The key is, if you see an acid and an amine in the presence of DCC, are you going to make an amide? And you make the amide by removing H and OH And just remember the DCC is what collects the H and OH. If there were no DCC, in other words, no catalyst, most people are going to think, well, no catalyst, then no reaction. But now comes the tricky part in if acids are acidic, check, and amines are basic, check, will they react with each other? So now you've got to recognize I've got an acid, got an amine, I don't have my catalyst, but I am going to get a reaction. It's what we would say it's not synthetically useful. So we're not making a group, just doing an acid-base reaction. And hopefully from general chemistry days, who has the protons? Or they start over. Is acid-base chemistry all about moving a proton? And who has the protons? Acids. And who tends to accept protons? Bases. But now we're just doing it with organic molecules. So will the proton always move from acid to base? And what is equally troubling is if you're asked for the mechanism, do you have to think backwards? Because do mechanisms show movement of positive things or movements of electron pairs which are negatives? So it's good to think about it both ways, but you really have to decide which way you're going to first think about it. If you want to think about it as just the acidic molecule is always going to give up the proton to the basic molecule. So if you want to try to memorize stuff, acids give up protons to bases. This is the hydrogen, which is going to be the proton. The proton is going to end up on the nitrogen of the base. So that's going to produce that amine salt, and then the conjugate base of this acid is going to be the carboxylate salt. So would this be synthetically useful or just an acid-base reaction? Just an acid-base reaction. So if the test question says student tried to prepare an amide, forgot the catalyst, what would be produced instead? Nothing, or this quote unquote salt. And why would we call this the salt? Because it has a negative and positive ion in it, just like an ionic bond. So if we were trying to make this amide, would this be helpful? No. What would we do to make this amide instead? Use the catalyst. Of course, if you're asked for a mechanism for how that happens, we should recall that amines are basic because the nitrogen has a lone pair of electrons. And carboxylic acids are acidic because this H is connected to a relatively electronegative O. And so if you're asked for the mechanism about how a proton moves, don't move the proton, you grab the proton with the lone pair. And so this arrow is making this new bond. And if this N is using a lone pair to grab the H, which way do those electrons have to go? To the O. And thus, would that O now have 3 pairs and a negative charge? And you could also be asked, why is that O stabilized through resonance? All sorts of questions. So that's the basics of what esters and amides are, how they name, how we name them, and how they're made. So what we're going to do now is practice. Before I erase it, what we're going to practice is the hydrolysis reaction. So if we utilize an interesting molecule to illustrate hydrolysis, while it's up there, we can also illustrate another important part about amine chemistry. Would we say this molecule has an amine group? And is that amine group primary, secondary, or tertiary?
Secondary?
Tertiary, because that's a C, that's a C, and that's a C. So if you have 3 carbon groups on a nitrogen, it's a tertiary amine. Would you say this is an ester?
Yes.
But atom is right here, because that's the one that people sometimes miss. That's a carbon. And would we say it's also another ester?
Yes.
And so if I say in that molecule, how many ester groups?
2.
If we say locate the ester bond. Gotta fix that typo. On this ester, that's the ester bond.
Yeah.
On this ester, that or that is the ester bond.
The one on the left.
That's your ester bond. So you could be asked a myriad of questions with that, like, does that molecule have an alcohol? No. Does it have an amine group? Does it have a carboxylic acid group? No. Does it have an amide group? No. Does it have a group which has basic tendencies? Group would that be? The amine. So that nitrogen, which makes it an amine, gives that molecule basic properties. So if we just showed that molecule some HCl, would you say something's going to happen or nothing's going to happen? something's gonna happen. And what would happen if you have a base and an acid?
You get a salt.
You get a salt by proton transfer. And who's gonna give up the proton? The acid. Who's gonna take in the proton? The base. So
The
you would
base.
agree your carbon skeleton and now you would put an additional proton on the nitrogen, and of course, the nitrogen would pick up the positive charge, and the chloride would be negative. And if you were asked for a mechanism for how that happened, redraw your HCl with its full Lewis structure, then how would you show the nitrogen using its lone pair as a base? And if that starts it all off, does this bond have to break? And which way are those electrons going to go?
Towards the Cl.
And so do those two electron movements account for these two species?
Mm-hmm.
And to be fully correct, should you put all the dots on the chloride?
Okay.
So which one would we call the salt? The one on the right, which one would we call the free base?
The Cl.
This is the free base because the amine has its lone pair of electrons still free to act as a base. This would be the salt because it's got an ionic bond. That's a relevant example in today's society, as one of those would be crack and one of those would be powdered cocaine. So which one would you say is crack, aka free base?
Free base.
This is crack. And this would be your powdered cocaine. Which one would you, if you used cocaine, smoke or inject?
The crack.
Which one would you snort?
The cocaine.
The hydrochloride. More relevant to what we're interested in, which one's more water soluble?
The second one.
The hydrochloride salt, which is why if you tried to snort this, what would happen? Not the intended effect, because the free base isn't water soluble, so it's not going to get taken up by the body quick through the mucous membrane. So that's the actual structure of cocaine. So would we say these are two different molecules, or would we call them two different forms of the same molecule? I would call them two different forms of the same molecule, and is the molecule cocaine? Could they have very different effects on the body? Because they're different molecules or because of how it gets assimilated? So if you're a freebaser, does the cocaine go directly to the brain through the bloodstream? So would you get a fast action? And that sort of explains why freebasing is so addictive. Enough on that. That's just illustrative of being able to act as a base, reacting with an acid to make a salt.
So what is the name of this reaction again?
It doesn't really have a name reaction. It's just acid-base chemistry of amines, what I would call it.
Okay. So this one is different than this DCC one, right? This one is HCl.
Yeah, the DCC was making an amide.
Okay.
This is totally different.
Okay.
So if we compare this to this, now the intent is totally different. If you see water and acid or HCl, now you should think you're doing or attempting to do hydrolysis. So now it's important to remember which two functional groups are hydrolyzable. So the two functional groups that hydrolyze are esters and
Amides.
so if you see this condition, you got to recognize those are hydrolysis conditions. You've got to know or look for esters and amides. So do we have any amides in there? No. Do we have esters in there? So once you recognize this is an ester, that's an ester, do you now know those two ester groups are going to hydrolyze? So when we do hydrolysis, we're going to add H and OH across the ester bond. So now you should go into this ester and find the ester group. So the ester bond is that one. We're going to chop it. And then you ask yourself, what do you add to that C? You're either going to add H or OH. And at the same time, ask yourself, what are you going to add to that O? Because that's the bond you're going to break. So you got to add something to C and something to O. For most brains, it's going to be easiest to see if you add H to this O, did you generate an alcohol? That should send off light bulbs because esters are composites of alcohols and acids. And then following in turn, if you add an OH to that C, do you generate an acid? So then you should redraw your carbon skeleton. With this bond not shown anymore, what are you going to add to that C? OH. What are you going to add to that O? H. And now this methanol is separated from this new molecule. Not done yet because you have another ester group right there. Find your ester bond. So is it there, or there? Of those four bonds, which one is what we call the ester bond? Right there. And if that bond makes it susceptible to hydrolysis, you're going to chop it. And you just have to ask yourself, which atom of the ester bond gets H and which atom gets OH? So which atom gets H? The O. Which atom gets OH? The C. Redraw your carbon skeleton. Are you going to show this bond? Yes. And does this O pick up the H? And what does this C pick up? The OH. And so you'll now have those three molecules, methanol, this, and this, which came from this one molecule. And that happens because this molecule has two ester groups which both hydrolyze. Unfortunately, you're not done yet, because now you have to take into account the conditions. So once you're done with your hydrolysis, ask yourself, what are my conditions? Acidic or basic? They're acidic. And which functional groups will change their form in acid? Basic functional group. And which is our only basic functional group? The amine. And so are any of these amines. And so what would happen to this nitrogen because you've done your hydrolysis in acid? That nitrogen would pick up an extra proton and a positive charge. So if we hydrolyze cocaine in the presence of acid, are we going to get those three molecular species produced? All right, one more time, a little faster. That's again our cocaine molecule. If we now do our hydrolysis in the presence of base, so again, we're going to see base shown like that or like that, either way. The key is first do your hydrolysis. So taking the same approach we just did, what groups are susceptible to hydrolysis? Esters and amides. So do we have esters or amides in our molecule? Yes, how many? There's an ester, there's an ester. Next up, find the ester bond and chop it. There's an ester bond, there's an ester bond. We're going to break it. This atom is going to get OH. This atom is going to get H. This atom is going to get H. This atom is going to get OH. Been there the whole time. Now we're going to redraw the product. So how many molecules are we going to get from this one? 3. This atom is going to get H. So do we have methanol? This atom is going to get OH. So do we have benzoic acid? And then this whole molecule, the carbon skeleton remains. Only this atom is going to get OH, and this atom is going to get H. So there's your initially formed hydrolysis products. So there'll be 3 different molecules. And then lastly, go back and check what are your conditions. Your conditions are basic, because hydrolysis can be catalyzed by acid or base. In this case, we're catalyzing by base. So of these products, are any of them acidic? If so, will those functional groups that are acidic lose a proton? So is this acidic or will it stay as methanol? That'll stay. Is this molecule got any acidity? There's a carboxylic acid, so what will happen to it in the presence of base? Lose a proton and it will exist as the carboxylate. And if you are shown this, that you should show the sodium counterion. If you're just talking about hydroxide, then you don't have to show the sodium. And is this molecule an acid? And so what will happen to its H goes away, and we would have those three products formed in base. Fun, what would happen if we threw that whole mixture back to acid? This would reprotonate. This would reprotonate. And the one that is hard to see and easy to miss is if these are your basic conditions and this nitrogen has its lone pair, if you throw all of those in acid, what will the nitrogen do? Pick up an extra proton and be present as its saltful. So hydrolysis of cocaine in base will produce those. And if we did it in acid, it would produce those three. So that's why the acid-base chemistry of amines and acids is so important, because it actually changes the form of the molecules that are produced. All right, on Monday, we're going to go through the macromolecules handout, which is about carbohydrates, lipids, proteins. That's all I got for you today.
Thank you.
Okay, y'all, have a good one.
Thank you, Professor.
Okay, Tia Rose, where are you today?
I'm on my way back to California. Look, I'll show you a little picture of where I am. But we have a balcony. I can turn it around.
Anyone want to see Tia Rose's room?
We're at sea.
It's, oh my gosh, that's gorgeous.
I'm
That's
sorry.
We're jealous.
We're at sea.
Bye, Tasha. Okay,
I'm sorry.
End it. I'm going to end it. You have a great rest of your trip.
Bye.
Thank you. Could you see the water?
Yes, it's beautiful.
Okay. Okay. Okay,
I'll
thank
post the
you.
recording. Okay, bye now.
Okay, bye-bye. Look, you probably saw